first part of the question is just a 65 kilonewton load subjected to this parallel configuration, and it was experiencing 65 kilonewton compression, and we needed to determine the stress. Just give me a minute. Okay, and so therefore, now we have to look at the temperature loading now, which is a different type of loading. So now, if you look at the setup over here, right, and this applies to the one we've also looked at. If we heat the ball with the temperature load, right, material 1 is assumed to have a higher coefficient of loading expansion, therefore it will extend by the change in length 1, right? Then material number 2 will also exchange by the change in length L2 mentioned here. So what's important here to note that the one is longer than the other one due to the higher thermal coefficient of expansion. But now when we fix it, meaning we fix it over here, like where this is over here, you'll notice that if you compare from this point, there'll be there's an x1, right? And then there's an x2. So if you draw a line from here going right down, you'll notice that this piece over here, right, this part here, if it's fixed at this part, as this thing grows, number 1 will be compressed, right, because it's fixed. However, number 2 still needs to grow, and therefore, as it's connected to number 1, it will be in tension. So if you look at the actual sketch, you'll see L1 plus L1, change in L1 minus change in L2 is essentially equal to X1 plus X2. And the reason for this is that the final length must be the same because they are attached to each other. That's the key here, okay? So you don't have to essentially know all of this, but what is key is that you need to know the two things. The first thing is know that the forces are equal because they're both fixed, and the fixed part is essentially the reason why the materials are getting stressed because it's being compressed or being pulled, whatever. And then if you just clean up the formula for the expansion part, which you discussed over here, if you look at the sketch, the change in L minus the change in length 2 must be equal to x1 plus x2, as you can see over here. And then you take length as a common factor, and you basically have this equation over here. This equation works assuming that alpha 1 is a higher linear coefficient of expansion. So this is the equation we're going to be using now. And that's for an increase in temperature. I do want to make you aware, if you go to this part as well, a decrease looks a bit differently when you're over there, right? So just be aware for that's in parallel. However, most questions are always talking to when things are essentially increased. So I'm just making where there is a difference between the two. And then if you want the final length of the ball, depending on which material you use, again, it's nearly the same as the other one. You take the original length, you add a thermal expansion, and then you minus the mechanical aspect due to the compression. However, for material 2, it's going to be the original plus a thermal plus x2. And the reason why you're adding x2 instead of subtracting, because remember, it's this piece over here. So understanding the sketch is key to knowing the problem. However, if you do understand this formula, you're going to be fine. So what I'm going to do now, I'm just going to snip this formula, and we're just going to apply it straight away. All right. So what we're going to be doing now, we're going to be looking at the second part of that question. Okay, cool. So let me just place it here. All right, so I'm just going to put it here, and then we're gonna work through it. So I'll just move this to the side here. So I'll just keep him here and we'll work with him. So again, the first question, we had to work out the change in length or the final length. And what is key here, just the stresses. So we knew due to 65 kilonewton load, it experienced a stress of 167.27 megapascals and the copper experienced 112.8. So now, what's the next part of the question? It says, if the compound mentioned 1.1 was loaded through the night and experienced a change in temperature of 37 degrees, right? So now there's a change in 37 degrees. They give us a coefficient of linear expansion for both. You find that copper is more than steel. And it says, refer to calculation to the previous one and calculate the following. The resultant stress developed in each material when considering 65 kilonewton load and the change in temperature. So what we do now, we're going to first find the stress induced due to the temperature. Once we do that, then we're going to need our stresses in the previous question. So let's quickly get to that. So how do we do this? So if you remember the previous one as well, all we basically need is this formula over here, and then we can find our our force. And once you have a force, we can find our stresses. So if you look at the formula, I'll write it down for you. Just again, it'll be alpha 1. Remember, alpha 1 is always the bigger one. T, change in T, delta T, will be equal to F, open bracket, 1 over AE, and that's the steel. So let's just call this steel. No, let's just call this copper, and that's steel. And this will be of the steel plus we have 1 over AE, and this will be of the copper. Okay, so what I want you to do now, using these values, I wanted to just populate this. Let me just bring the question down. So if you look there, copper has a linear expansion of 18 times 10 to the negative 6. Steel has 12 times 10 to the negative 6. And we experience a temperature change of 37 degrees, right? It's fine. Remember, we're looking for the force. Then obviously over here, we're going to need our AE for both. So look at your previous question as to what was the A and the E. So if you recall, it was this over here, basically 215, and that for the steel, and then 145 for the copper. So what I want you guys to do for me now is just calculate, I guess, the left-hand side, and then you can do the right-hand side, and the only unknown will be F. So Busi, can we get the left-hand side? Welcome, Rafika. We're going to do left-hand side, we're going to do right-hand side.
The left-hand side say I got 222 times 10 to the power negative 6.
222.
Yes, sir.
Like this, like that. Okay, that's fine.
Times 10 to the power negative 6.
It's fine. 3 or 6, negative 6, no?
Yes, sir.
Okay, now you must do this one, but you must do this one with yesterday's question. So, you know, the steel of yesterday was 215, the area, the same, you know what I mean? The same thing here. The same values of yesterday's questions. The 215 and I can't remember the other one. Yeah.
Can you see the values for yesterday, sir?
Don't you have your book there? The values are over here. I don't know if you can see them. There they are.
215.
You got them?
Yes, sir.
Aiden, what did you get? Are you still busy as well?
I'm still calculating, sir.
Okay.
So I got 4,827
Got you. I'm with you. 4,827. 4,827. Yeah.
times 10 to the power of -8.
-8. Okay. So then find the force for me. What is the force? I'll check the answer now myself as well. Just calculate it.
The force is 4,599 kilonewtons.
It's just 4, yeah, say again 4,599.
4,599
Yeah, that looks
kilonewtons.
about, yeah, that looks right. 4,599 kilonewtons. That looks good. Then we want to find the stress of steel. Can we just call it stress steel TS, which means thermal, and then TC, which is copper. So all you must do is take the force, and when the force is equal for both, and you divide it by the respective area. So the area of steel, which you have there, and then 4.599. So you can see it's two different forces and stresses you're getting now, as compared to when you do the mechanical part. So let's just get that stresses. So it'll be something MPa, and then I'd like to know what are the sensors of both. That is what I want to know. Whether they're tensile or compressor.
For copper is 14,639
14, what's it?
megapascal.
639.
14,639, yes, sir.
Okay. It's a tensile compressor. That's very important. Okay, give me the steel. It's fine. What's the steel value?
Constant. 26,025.
Okay, 26,025. Colleagues, you all get this answer? Before I move on. We all get that answer. Just gonna paste this here for now. So I want just to remember, we all get that answer before I move on. It's fixed over here.
Yes, sir.
Okay, perfect. So let's look at the sketch again. Obviously, our thing looks slightly different. This is vertical, but this is horizontal. So when I'm talking about the sensors, right? Which material is being compressed after the expansion? Which one? Material 1 or 2? That's fixed over here as well.
Material 1, I think so.
Exactly. It is being, so it's being compressed over here, right? Therefore, you find that the one with the higher linear co-expansion is going to be compressed. The reason being because it's extending a lot faster or expanding a lot faster than the other one. So copper will be C. This one over here, if you compare the two over here, obviously at this piece, this one is attached to the other one, and long story short, the steel will be basically in tension, right? Just got to read your note and then go find about that. So what's key? What you're going to pick up just as a shorthand, the one which extends fast essentially gets the Hofferts, gets compressed, the other one's attached to the other one, and obviously it kind of pulls it along. I don't know if that makes sense to you. And it pulls material two along, therefore it's in tension. So what I want to do now, right? The question is not done. So that's the temperature part. They want the resultant stress developed. How do we get the resultant stress? It's simple. So you just pull up a table like that. Okay. You just do a table like this. You want to perhaps maybe do, how should I do it? Let me just see here. Okay, something like that. You want to put in, let's say you want to put in steel. You want to put in copper. And you want to put in say, the mechanical loading. You want to put in the thermal. And then at the bottom, like another, just extend this a bit further. It's 4 columns. And you can put in the resultant. So this is stress here. Okay, stress, and that's the resultant. Okay, let me know when you're done with the table. Just bear with my table over here. So this is basically 1.1 and then 1.2. So once you're done, just let me know. And then what I want you to do is to read the stress values and the sensors as well, right? Meaning whether it's compressive or negative, compressive or tensile. Just want to make more space. Okay, not like that. Something like that. Let me just let me know if you're done with the table. Okay, perfect. So once you're done, just let me know, and then we can move on.
Answer.
Okay, cool. So Ada, can you read your values for 1.1 for steel and tell me the sense as well? Steel and copper.
So you can,
in the first.
so you can,
Yeah. Can you read me the
say
stress values? The stress values, right?
Huh?
For the steel in 1.1, which you got yesterday.
Oh, that is going to be, the stress values is going to be for
Yeah.
for the steel is 167.27 megapascal.
Okay, I don't have to put the MPa, that's fine. My question was compressible tensile.
The steel is going to be tensile.
No, for the first part, 1.1. For 1.1. Should we go back?
It's compressor.
You understand what I mean? At this part over here, you see it? It's been
Yeah.
compressed, right? Yeah,
Compressed.
that's what I'm talking about. Okay, and we had it down here. It's compressed, okay?
Mm.
And the copper is also compressed, am I right? Due to the
Yes, sir.
65 kilonewton load. Yeah, so that's 100 amps again. 112.815.
0.815.
And remember, compressive sense is negative, no? Anything negative is deemed to be compressive. Everyone does know that, right? Is that fine? So that's due to the 65 kilonewton load. This is due to the change in temperature. So can I get, okay, so what I do now, I go to these over here. So I look at my stress due to the thermal expansion, right? This is 26. But remember, it's tensile, like we said. Is that fine? We make that plus. Then we come to the thermal side here. That's negative. That's 14.639. You guys got that? Is that okay? Is there any questions up to this point of where we got the values? Why is it positive? Why is it negative? Things like that.
We got it, sir.
You got it now? So don't be confused between the two. So the first part was due to the 65 kilonewton, being compressed. That's the module 2 part. Now the module 3 part is now the new thermal part. And in parallel, the sensors are different. All you must do now, colleagues, add these two up. So the 1 minus 67 plus that, and add minus 1112 minus obviously 14.69. So give me these values at the end, bottom.
Sorry, sir. Do we minus
Yes.
the thermal from the mechanical or
You're adding them up. That's the resultant.
okay?
So what I'm saying is 1 minus 67 minus 167.27 plus 26.025. You're saying minus 1112.81 plus negative 14.639. Obviously, that's negative minus negative. You know what I mean? So what is this one over here? And what is that one over there? And this would be an MPa. So what do we get for this one? What's the resultant stress in the steel due to both loadings?
Steel is going to be negative 141.245.
Yeah, 245 MPa. Or we can just say it's 141.245 MPa per compressor, right? You agree with me?
Yes, sir.
Yeah.
Yes, sir.
And then we can do, obviously this one is also going to be compressed as well.
That's going to be negative 127.
Negative 127.449.
449.
Okay, 449 MPa. And of course, the resultant stress is also be 127.449 compressive. Am I right?
Yes, sir.
Okay. Very important question, guys. I highly recommend you go over this again. So there we go. We found the resultant stresses. So again, I want to be clear in what I mean by this. It's a lot of work. The first part, sometimes the questions don't specify. They might ask you to do the temperature first, and then you must do the loading condition next, but the principles are the same. So just be aware, two different types of thinking is coming. So the last part is the final length of the compound bore under the mentioned conditions. Like I said to you, it's nothing crazy. I'll just paste it here for you. So you can actually see, and it's quite simple. If you understand that sketch, everything kind of makes sense. And I'll place it here for you. So all you have to basically do is take the original length for material 1 plus the thermal expansion minus the elongation, the FLEA. But if you're working with material 2, which has a lower linear expansion, you're going to have to add, because remember it's in tensile. So just be aware why this is like that, which is all talking to the sketch. So what I want you guys to quickly do for me, get the final length. You can use either material 1 or material 2. It'll be exactly the same. Okay, maybe just use it here. So material 1's length, I believe, was, let me use black. It was 0.127, right? Plus that expansion was how much again? Was it 12, eh? That's how much it was steel? I can't remember. You guys just read the values to me. Steel is 12, okay? 12 plus 12 times 10 to the negative 6 times the length of how much again? It's 0.127 times, okay, the gray wasn't such a good idea, it seems now, times the 37 degrees. Then remember, now we must minus x, which is essentially FLEA. Now, what is important when you do this part, the force you're using is not of the thermal one, right? It's of the 65 kilonewton one. Am I clear to everyone which force you must be using for this part over here?
Can you say that again, sir?
So what I'm saying is, when you're finding the elongation here, right, this x1, right? The force you should be using is the force which you find over here. Where is it now? You see this one over here, 29.55. You see that one over there.
Okay, sir.
Yeah, I'm pretty sure. Let me just confirm. Yeah, you can't use the other force. Let me just check again quickly. Yeah, no. Okay, no, I'm wrong. Okay, so the force you must use is, you want to use this force here, sorry, use this force over here. Forgive me for that one. That's how I was doubting myself. You want to use this force over here, that one there, the 26. Under the 26, the 4.599. So everything's on the thermal side. Forgive me for that one. So let me just quickly do that one. So this would be 4.599. So everything on the thermal side, that's fine. 4.599 kilonewtons. The length is 0.127. That doesn't change. Then we have 215, I believe. Then we have an area of pi over 4 times 0.015 squared. Okay. So forgive me here. So you must just use the force of the temperature, not the previous one. So let's get that, the final length after everything has been, yeah, I've got the answer right here. I'm thinking of something is just bothering me, but anyway, no wonder. Yeah. Because this other answer should be roughly the same. Okay, so what is my final length? So what do we?
So I got 0.12704.
0.12704. Yeah, that's fine. Is that a slight increase, I believe, huh? That is for the first one, huh?
Yes, sir.
Okay, let me just confirm this here. Change it lens. This is my wait, guys, I made a mistake. You're making my mind. So remember, this is the copper one, remember? The copper one is number one. So there should be what is it again? It's 100 and I did it for the wrong one. Copper should be 145, sorry, and the diameter is, just keep your calculator there, and the diameter was 20. Yeah, my bad. 145. Remember, we're dealing with length one, which is the copper, right? Did I choose steel over here? I see. Okay. I wanted to do copper, man. So that's 145 times 10 to the power 9. If it was steel, I should have put it up with me. Maybe you can just change it plus, you can actually get the proper value. Instead of me changing all of this. So let me just change this to 0.02 squared. I just realized now we're doing the L1. And copper's linear of expansion, I believe, was 18, if I'm right. 18 times 10. Okay, that's right now. Check now for me. I hope you guys are with me or that or not. I just want to confirm the linear expansion again. Is it 18? Yeah, okay. Now let's quickly see what we get here. And I'll prep this one so long. 0.127 plus 12. 0.127 times 37. Then over here it's plus the 4.5. It's basically what I had before, but just the plus now. That should be 215. Yeah. Who's the item? Did you guys get it? So what I'm saying is this. Yeah.
The first one is going to be 0.12707.
Yeah. 07. Okay. So we're saying we increased a bit here, right?
Yeah.
Let's see this one over here. Feeling we're so sus for that one. Just make sure you got all the right values in. It should be the same. That's what I'm trying to show. Very close. Not sure of that first one. I'll just check on my calculator quickly. $18. Oh.
Second one is more or less the same. So it's
It's the same, huh?
0.12704.
104. Okay. So we're out a bit here. I'm just confirming. Aiden's one. Yeah, it should be close, very close. It should be like even 6.5. That's what I'm looking for. 0012 squared. I'm just confirming. Yeah, okay, I see it is 0.2707. Yeah, okay. It should be nearly the same. Let me just change this one to 20. What's it? 18, and this one is 12. Okay, this one must be 215. I'm just doing the second one as well. Yeah, okay, it's not exactly, but it's close enough. Okay, and obviously this is in meters. Yeah. Just feeling a bit sus with this, but anyway, that's okay. All right, colleagues, that's basically it. We're at the end of the session. I did say we're just going to have a small one to continue. Sorry, guys. I've been talking all the time to myself. I'm sending you a homework question to do. I think it's coming from 2024, 2025 paper. So please do that for homework. Is there any questions with this section before we close off? Any place of uncertainty which we can address? Aiden, Sipiwe, Busi, yep.
No, sir.
You good?
No, sir, I'm good.
You sure? Yeah. So
Yes,
what
sir.
you can do is do question 3, like you can do it now. And just be aware of question 3. It says 40 degrees to 110 degrees. So obviously you want to take the difference. So there's a change in temperature of 70 degrees, right? So try that one. It's 14 marks. And what's nice with this one, you don't have what's the word I'm looking for? You don't have an additional load though. You just have a normal, you know what I mean? A normal, just temperature. But anyway, guys, let me know. Post your answers in the group and we can engage on that one. But cheers, guys. Thank you very much.
Thank you, sir.
Cheers,
Thank
cheers.
you.